plasma. And we even bounced that idea around of like, cold cutting processes. So what we did is, we took that and then we put it into we designed a methodology, which is listed there. 4 tasks. The first one, the Oxyfuel Cutting process, I think there was about 20 different variables that we wanted to screen. So we cut that into a 2-task approach. So in the first task, we screened out, we did a screening DOE where we basically identified, what's significant here and what isn't. And then the next task, we took what was significant, put it into a DOE, ran that DOE, and then determined what our optimal conditions were. And then in task 3 and task 4, we looked at benchmarking where the plasma arc cutting process is with respect to oxyfuel cutting and also laser cutting process. So here are the general cutting process requirements. I will cover these at the end as far as which processes are capable of meeting these. So capable of cutting in all positions. You have to get the cut piece out. The target envelope for the target cut piece is 8 foot by 15 foot. So curve width becomes an important thing. You have to be able to get that part out easily. Safety is also another important factor. And the current travel speed for the oxyfuel cutting process that's being used is about 10 inches per minute. So we also looked at what our travel speed capabilities are with other processes. So opacity is not something that's normally measured in a laboratory type environment. So we had to design a system for comparing opacities produced by through different trials. So what we did here is we designed this cutting system that consisted of a fume hood, and then the fume was pulled through the ductwork, which was pulled by a blower fan. And that had a variable speed damper on it so that we could set the flow rate constant. And then in the background, it's probably hard to see, but the computer basically captured all the data for us. So we hit the go button, did the cutting trial, and the computer captured the opacity data and temperature data. So in this ductwork right here is where we measured our opacity. So we had a transducer set up that, an opacity light source type setup that measured the opacity across the duct. And then we had a temperature and air velocity sensor. The real thing that we captured here was opacity. We also captured the other data, but we couldn't really correlate temperature and air velocity very well. So those were more, it's easy and it's easy to capture. It's cheap to capture, so capture it in case you ever want to look at it again. So what we got was we got opacity as a function of time. So we did our trials. We put everything on a thumb drive and sent it over to Penn State where they analyzed it. And how they analyzed it is they took you had a baseline starting condition that maybe is above 0 most of the time. So they zeroed out the opacity graph, and then they captured 2 things. They captured average opacity, and then they captured total opacity. What total opacity is it's a percent opacity dash second. So they basically added it up for all opacity values over every quarter of a second. So for the oxyfuel cutting screening DOE, we looked at fuel gases, 5 different types of fuel gases, 4 torch types, 3 different tip sizes, plate surface condition, plate thickness. A little mention on the fuel gases. What's currently being used is propane in the shipyard. We also looked at propane, methane, and even gasoline. Petrogen it's called a Petrogen system. It's a gasoline-based system. Magnagas was a product that was identified by the shipyard that was of interest. Basically, it's recycled waste, liquid waste, and they have a plasma process that turns it into basically a gas that contains about 66% hydrogen. So we looked at that as well. It's marketed as a green technology. And torch types, we classified it for the screening DOE. We classified it into standard and non-standard. So the output of this was a 16-run DOE with 2 runs with the baseline condition that's currently being used. And then the Petrogen, due to the design of the system, didn't quite fit the model of the DOE, so we added a couple of trials for that instead of having it inside the DOE. So for our results, I'm sorry, I mentioned I forgot a key point here. The plate surface condition. So our target applications are aircraft carriers. Aircraft carriers generally have half-inch thick material. But the shipyard also threw in 2-inch thick material. You had 2-inch thick clean, which wasn't painted, and then you have what we're calling 2-inch painted. And that's shown here. And then on the front side, you had vintage paint, and on the back side, you had the residue from where the SHT, the special hull treatment tile, was. So that was on the back side. So that was pretty significantly different than what our half-inch painted was, which was basically the half-inch painted was just it was a little bit too thin in comparison to what was in the shipyard. It was about 0.02 of an inch thick paint. So one of the findings was that the 2-inch thick for the 2-inch thick painted plates, the results of that, the painted, basically the surface hull treatment tile, it was a lot thicker, so it kind of it was a dominating factor in the DOE. But we also, however, we got good information out of it, and we were able to identify what was significant and what wasn't. So the significant factors, the non-standard torch types produced the lowest opacity. Because it was a screening DOE, we had to run about 4 extra trials to figure out which non-standard torch type produced the lowest opacity. And propane and methane gas were identified as having equally low opacity levels. In addition to with the 4 extra trials, we couldn't distinguish from the data which one was better. So we carried both of them into the next phase. And something that's of big interest to the shipyards is they're very curious about how tip size affects it. So if they can use a bigger tip size, it's better from a cutting standpoint because it produces a wider curve. And what we found here was that tip sizes wasn't a significant factor. So moving on to the process optimization DOE, what we plugged in here is we had surface, gas type, paint thickness, and tip size. We carried tip size over, even though we found that it wasn't significant, we carried it over to verify that it wasn't. For paint thickness, we had rusted, which obviously isn't painted, and then we had what we call thin paint and thick paint. So we took a bunch of plates and we put on half of them we put 15 thousandths inch thick paint on both sides, and on half of them we put 30 thousandths inch thick paint. So this is representative of what's actually in the shipyards. So that was our paint thickness condition. Gas types, propane and methane gas. Nominal fuel O2 pressure. So we had a low setting and we had a high setting for each fuel gas. So what was generated from this was, robustness plots and a model were generated from the DOE data. And you can see that the most significant factor which is shown here in red, is paint thickness. So basically thicker paint the thickest paint produces the highest opacity, followed by the thin paint, and the lowest is produced by the rusted condition. The blue line here, it represents tip size, and again, tip size was demonstrated to not be a significant factor. The green line is shown by fuel O2 pressure. Lower fuel and O2 pressure produces lower opacity. And the dotted blue line is the surface condition. The clean data from the previous DOE, from the Task 1 DOE, was also included on this graph. And again, clean produces less opacity than rusted, followed by paint. So what we got from this is we identified a set of optimized conditions. And we identified it both for both fuel gases. We found that fuel gas, between the propane and the magnet gas, fuel gas wasn't, that wasn't significant. One did produce significantly lower opacity than the other, pretty equal. So we generated optimized conditions from our DOE data for both gases. Magnet gas is a new product. Whether the shipyard accepts, it's up to them. There's trials going on now. There's work being done right now in the shipyard to evaluate both gases more. But we gave them two options. We gave them, the best conditions for propane and the best conditions for magnet gas. Another recommendation is that petrogen, on the data for the 2-inch thick painted plate in the first DOE was largely disregarded. Well, I'm sorry, it wasn't disregarded, but the petrogen system, it's a gasoline-based system, so the shipyard was hesitant to carry it into the next phase because it was a gasoline-based system. Getting that approved in the shipyard, it's going to be really tough. So we discarded it, but a really interesting point was that on the 2-inch thick painted plates, which had that SHT tile on the backside, this is by far the most, what's the right word? This is kind of the worst case scenario for cutting. And the petrogen produced lower opacity for that particular surface condition than the other gases. So it's worthwhile to reevaluate petrogen. And I would suggest doing it on something that's got a fairly thick paint on it. What else is there? So the torch design, what we found was that the Harris has a low flow torch, and the low flow torch was shown to produce the lowest opacity, and we need to figure out why it produces the lowest opacity. And just for the record, we don't endorse any products. So, I want to be on record for that because we don't have any. We just literally ordered these torches from the vendors based off of what the shipyard told us they were interested in. So I'm not selling any products here. So moving on to plasma arc cutting. In 1999, there was work done where they looked at reducing fume for plasma arc cutting. What was identified, shielding gases were mentioned in this report, with the lowest fume being generated by what they call H35, which is argon with 35% hydrogen. Yeah, it's H35. Argon with 35% hydrogen. That produces the lowest fume with the plasma process. The two mix together, so you have nitrogen produces the second lowest amount of fume, and oxygen or air produces the highest amount of fume. So we carried that information into our work, and we looked at those. We looked at 3 different plasma and shielding gas combinations. We looked at air-air, which is your cheapest option. We looked at H35 and nitrogen. H35 for the plasma gas, nitrogen for the shield. And we looked at H35 for both. And we looked at the same three surface conditions. We looked at rusted, and then we looked at thin paint, and then we looked at thick plate. So the constants that were held for all 3 gases are listed there. An important one is that we had to weave with this process. If we did a stringer bead type approach where it's just without weaving, the dross would bridge around the backside. So We used a weave technique, and the kerf width was around 0.2 inches, 0.25 inches. So again, robustness plots were generated along with predicted best case conditions. So surface condition is shown. What is surface conditions now on that chart? Yeah, it does. Plate surface is shown by blue in the blue. Again, we saw the same trend where rusted produces the lowest, and as you thicken up the organic layer on the surface, you get significantly more opacity. So the rusted, the average opacity, basically for each surface condition, the average opacity was quite a bit higher than it was for, or was higher anyway, than it was for the best case oxyfuel, for the best developed oxyfuel cutting conditions. You can see with air, combination of air, and thick paint, you generated the highest opacity. So in the next task, what we focused on was laser cutting. And we just wanted to, basically, we didn't optimize the laser cutting process, but we wanted to get baseline conditions just that we have something to compare it to what we got for oxyfuel cutting and plasma. So the materials, again, we looked at 1/2 inch thick, rusted, thin paint, and thick paint. And we did some preliminary trials, and we looked at to develop our cutting conditions. And we found that a power to travel speed ratio of 0.1 generally resulted in the best cutting. So the results, the kerf width of all the trials was around 50 thousandths of an inch, which is too thin. A lot of the times the dross bridged around the backside, and so you did have dross bridging on the backside. So it wasn't a clean cut. And what we did to try to overcome that is we went down and then we went up. And that helped some as far as breaking up the dross, but it still had that bridge. Basically, the gap's just too narrow. Thin paint and thick paint, again, what we found was that the opacity level increases with the amount of organic matter along the surface. So, but the average opacity was the lowest for laser compared to the other two processes. So, a process comparison of the best settings. We had data for all three processes for rusted, and so the baseline condition produces an average opacity of about 0.9%. The best case conditions identified for each of the processes was about 50 to 60% lower than what it was for the baseline condition. The plot shown here is based on the best settings for each process and 1/2 inch thick plate. So the opacity results for the laser process were doubled because it was assumed that to use this in production, you have to do 2 cuts in order to get the 2 side-by-side cuts in order to get the plate out. So surface rust has less opacity than painted, but we can see here. And in general, the laser produces the lowest opacity, plasma tends to produce the highest opacity. For the effects of organic matter, the plot here is based on the best conditions for 1/2 inch thick plates. So the total volume of paint burn is calculated as 2 times the kerf width, times the paint thickness, times the cut length. And what we found here is that as we increase the amount of organic matter that we're burning, so if your kerf width is wider and you increase your paint thickness, then you're going to get higher opacity levels. So listed here is the criteria that was provided by the Shipyard, and all 3 processes are capable of conforming to 1, 3, and 4. Laser couldn't do 2 or 5. As it stands right now, lasers can't do 2, 5, or 6. You got to recognize though that the laser cutting process is not optimized by any means. So you definitely wouldn't disregard that process, because you give that to the the laser cutting guys, you know, the people that build equipment, I'm sure that they could figure out a way to get that done. So, but it is important that it does produce the lowest amount of opacity. And safety conditions for all three processes. Safety for the magnet gas, the shipyard's got to evaluate it. And for the plasma cutting, it's just mentioned that 200, they want a manual system, so 200 amps is the maximum current level that you can use. And laser, basically if you're going to employ this in a shipyard environment, right, you got to be able to contain your laser beam somehow. So it presents some safety concerns. So recommendations, oxyfuel cutting with propane or magnet gas is recommended as the near-term solution. We identified optimal conditions for each of those gases. In the future, should the parties involved decide that they need lower opacity as well, then laser would be something that laser can produce low opacity. Finally, petrogen, I mentioned this before, but on the 2 inch thick material with the highest level of organics will produce the lowest opacity. That's a point that's worth looking further into.